There's a rule in planetary science that's held firm for half a century. Lightning in space looks like lightning on Earth. White, blue, predictable. We've seen it on Jupiter dozens of times, and it always follows the script until December 30th, 2020, when that rule shattered. A flash of green, brilliant, impossible green, tore across Jupiter's northern storms at speeds that shouldn't exist. NASA's Juno spacecraft caught it for just a fraction of a second. And in that moment, everything we thought we understood about giant planets became a question mark. This isn't just unusual weather. This is a phenomenon that might rewrite the physics of how atmospheres work. December 30th, 2020. Juno makes its 31st close pass over Jupiter's cloud tops, skimming just 3,500 kilometers above the swirling chaos. Its instruments are designed to pierce through the storms, to see what no telescope from Earth ever could. Then it happens. A brief flash, green, brilliant, moving at speeds that seem impossible, even for a planet where winds scream at 600 kilometers per hour. The data gets transmitted back across 600 million kilometers of space. When scientists at NASA's Jet Propulsion Laboratory first see it, there's silence, then confusion, then excitement. Because lightning on Jupiter is supposed to look like lightning on Earth, blue or white from the methane and hydrogen in the atmosphere. But this is something else entirely. Here's what makes this so bizarre. Lightning, as we understand it, is electricity, pure and simple. When particles collide inside storm clouds, ice crystals, water droplets, whatever's floating around, they build up charge. Eventually, that charge has to go somewhere. It arcs through the atmosphere in a brilliant discharge we call lightning. On Earth, it's mostly blue-white because of nitrogen and oxygen in our air. On Jupiter, with an atmosphere that's 90% hydrogen and 10% helium, scientists expected similar colors. And for decades, that's exactly what they saw. Voyager caught it. Galileo caught it. Even Juno had documented dozens of regular lightning strikes in Jupiter's massive storms. But green lightning? That requires something different in the chemistry, something that emits light at a wavelength around 500 to 550 nanometers. And the leading theory? Ammonia. Jupiter's atmosphere is rich with it, floating in those massive cloud decks that give the planet its signature bands. When lightning tears through ammonia-laden clouds, it could excite the molecules in a way that produces that eerie green glow. But here's the catch. That's just the theory. Nobody's ever seen it confirmed? Until now. Now let's talk about speed. Because this isn't just about color, it's about velocity that seems to defy physics. The green flash Juno captured moved across the storms at a rate that suggests it's not your typical lightning bolt. Standard lightning on Jupiter, as violent as it is, follows predictable paths. It branches. It crawls through the clouds the way electricity naturally flows, seeking the path of least resistance. This green phenomenon? It shot across the storm system like a bullet, almost horizontal, like it was riding something. Maybe Jupiter's ferocious jet streams, which are rivers of wind that flow through the atmosphere at speeds that would tear apart anything on Earth. Imagine a lightning bolt catching a ride on a 400 km per hour wind current. It would stretch. It would glow longer. It would look exactly like what Juno saw, a streak of green fire racing across the pole. But there's another possibility that keeps scientists up at night. What if this isn't lightning at all? What if it's something we don't have a name for yet? A completely different kind of electrical discharge unique to gas giants. A phenomenon that only happens under the crushing pressures and exotic chemistry of Jupiter's interior. That's the question driving research right now. And it's not just academic curiosity. Understanding Jupiter's electrical behavior tells us about magnetic fields, atmospheric dynamics, and the fundamental nature of giant planets across the universe. While Juno was revealing Jupiter's secrets, something equally strange was happening 320 million kilometers away on Mars. NASA's Perseverance rover was rolling through Jezero crater when its microphones picked up something unexpected. Tiny crackling sounds. Static. Pops. At first, engineers thought it was equipment interference. Then they analyzed the audio signature, the pattern, the frequency. And they realized what they were hearing. Lightning. Miniature lightning, invisible to cameras, but distinct enough for sensitive instruments to detect. Mars has always been the planet we thought was too dry, too cold, too dead for weather like this. Its atmosphere is less than 1% the density of Earth's. There's barely any water vapor. The idea of Martian thunderstorms seemed absurd, but Perseverance proved otherwise. These tiny electrical discharges are happening in dust storms. Those massive planet-wide tempests that can last for months. When dust particles collide at high speeds, they generate static electricity. And when enough charge builds up, it arcs. It discharges. It creates lightning we can't see but can definitely hear. The implications are massive. If Mars, with its thin whisper of an atmosphere, can generate lightning, then the rules we thought applied to planetary weather are more flexible than we imagined. Every world with an atmosphere, no matter how thin, might be crackling with invisible electricity. And it changes how we think about future missions. Astronauts landing on Mars will need to account for electrical storms that could interfere with equipment, damage electronics, maybe even pose a direct hazard during dust season. The universe, it turns out, is far more electrified than we ever suspected. Now let's talk about Uranus and Neptune. For decades, we've called them ice giants. The textbooks label them that way. The classification seems simple. They're not rocky like Earth, not gas giants like Jupiter. They're something in between, filled with ices. But here's the twist. New research suggests that label might be completely wrong. Scientists analyzing data from Voyager 2, the only spacecraft to ever visit these distant worlds, combined it with advanced computer modeling and spectroscopic analysis. What they found challenges the entire framework. Uranus and Neptune aren't dominated by water ice, ammonia ice, or methane ice the way we thought. Instead, their interiors are likely filled with supersonic water, a bizarre state of matter that only exists under extreme pressure and temperature. It's part solid, part liquid. The oxygen atoms lock into a crystalline structure, while the hydrogen atoms flow freely like a liquid. It conducts electricity like metal, but flows like water. This isn't just a semantic change. This is fundamental. It means Uranus and Neptune aren't frozen worlds. They're dynamic, electrically active, potentially churning with flows and currents we can't even visualize. Their magnetic fields, which are wildly tilted and offset from their rotation axes, suddenly make more sense. Those fields are generated by supersonic water currents deep inside the planets, creating magnetospheres unlike anything else in the solar system. And if we've been wrong about the ice giants, what else have we misunderstood? How many other worlds are hiding their true nature behind convenient labels? The answer is probably most of them, because every time we look closer, every time we send a probe or analyze new data, the universe reveals that it's stranger and more complex than our best theories predicted. So what connects all of this? Jupiter's green lightning, Mars's tiny discharges, the misunderstood nature of Uranus and Neptune, its electricity, energy, the fundamental forces that shape worlds, drive weather, and create phenomena we're only just beginning to document. Every planet in our solar system is alive with electrical activity. Earth's lightning storms are just one flavor in a vast cosmic menu. Jupiter's ammonia-fueled green flashes, Mars's dust-generated static, Uranus and Neptune's supersonic currents generating twisted magnetic fields. Even Saturn has lightning in its storms. Cassini detected radio signatures called whistlers that indicate massive electrical discharges deep in the atmosphere. And here's the bigger picture. If our own solar system is this electrified, imagine what's happening on exoplanets. Gas giants orbiting close to their stars, baking under radiation. Super-Earths with thick atmospheres and unknown chemistry. Ice giants in distant orbits around alien suns. The universe isn't just a collection of rocks and gas. It's a network of electrical phenomena playing out on scales we're only beginning to measure. Every storm is a laboratory. Every lightning bolt is a data point. Every mysterious glow is a clue to something deeper. Juno's green lightning isn't an anomaly. It's a reminder. A signal flare from Jupiter saying, "You don't understand this place yet. Keep looking." That green flash over Jupiter's North Pole lasted less than a second, but it opened a door to questions that will take decades to answer. Is it ammonia chemistry creating that color? Is it a new kind of discharge riding the jet streams? Or is it something we haven't even theorized yet? Some electrical phenomenon unique to the crushing pressure and exotic conditions of a gas giant? NASA's Juno mission continues. Every orbit brings it screaming back over Jupiter's poles, its instruments scanning for another glimpse of that emerald fire. And when it catches it again, because it will, we'll be one step closer to understanding the electrical soul of the giant planet. Meanwhile, Perseverance keeps listening on Mars. Future missions to Uranus and Neptune are being planned. And every discovery adds another piece to the puzzle of how energy flows through the solar system. The green lightning was just the beginning. The real story is still being written, one flash at a time, across the storms of worlds we're only starting to truly see. And the universe? It's not done surprising us yet.